So we're going to finish up chapter 3 real fast and move into chapter 4. And so this is the next type of problem we're looking at. So for this example problem, a compound has nitrogen and oxygen, is decomposed and produces 24.5 grams of nitrogen and 70 grams of oxygen. What is the empirical formula? So remember, the empirical formula is the lowest ratio. So for compounds like C2H2 and C6H6, both of these, the empirical formula is CH. It's just the ratio of elements. So of course, this tells you some information, but doesn't tell you necessarily what the connectivity is. So it tells you the ratio of atoms. So how do you solve this problem? Well, one of the things I'm trying to get you guys to think right away is like moles, moles. Think about moles. So start off with 24.5 grams of nitrogen and 70 grams of oxygen. And here then you divide by, well, I guess I should do multiply. So mole nitrogen to 14.01 grams nitrogen. And where am I getting this 14.01? I'm getting it from the periodic table and that bottom number there. On this periodic table, it's 14.007. Let me look at the textbook here. This one says 14.01. The textbook says 14.01. So that's where I get the number from, is the bottom number of the periodic table. And same thing with oxygen. Mole oxygen to 16 grams oxygen. And we do both of those. And let me sneak ahead. And you get 1.75 moles of nitrogen and 4.38 moles of oxygen. So then you're like, all right, well, the empirical formula is going to be nitrogen 1.75 and oxygen 4.38. Like, I'm done, yay. The problem here is, though, so when you deal with atoms and molecules, you have to deal with a branch of mathematics called discrete mathematics. So it's not continuous mathematics. This is continuous mathematics. So there is no such thing as 1.75 nitrogen atoms. You only deal with whole nitrogen atoms. So kind of like when you say the average family has 2.3 children. I'm making these numbers up. What does 0.3 children look like? So, right, you only have whole numbers of humans. So just like humans, you have whole numbers of atoms. And a side note, it's a lot of fun to mess with mathematicians. So it's always fun to say, oh, math is amazing. It's not real. Which is not. In my opinion, it's not. It's a great model. It's not real. Okay, so now we have a ratio of 1.75 moles of nitrogen to 4.38 moles oxygen. What do? We divide both these numbers by 1.75. I can do this math in the head. This is going to be 1 mole nitrogen. And what is 4.38 divided by 1.75? This is going to be 2.5. So now we have nitrogen 1. We don't really need to have the 1, but I'm putting there for emphasis. Oxygen 2.5. We're like, yeah, there we go. And again, discrete mathematics, can't do that. So how do we get rid of that 0.5? We multiply everything by 2, and we get N2O5, or dinitrogen pentoxide. So multiply those by 2 to get rid of the 0.5. So how do I know to multiply that one by 2? Well, here are some common fractions. So right here, a half is 0.5. So you multiply 0.5 by 2 to get rid of that. If something is close to 0.33, depending on your sig figs, you multiply by 3 to get rid of that. If it's something that's close to 0.25, you multiply by 4. And if something is close to 0.2, you multiply by 5. So that's just the decimal places of fractions. So that's how you get rid of those decimal places when you do the empirical formula. Okay, so you get this. So recap with this. Actually, well, I'll go ahead and do the recap. So we are trying to find the empirical formula. It's the lowest ratio of atoms in the formula unit. And we're given that we have 2.45 grams of nitrogen and 70 grams of oxygen. So we convert that to moles, and we get a ratio of 1.75 moles of nitrogen to 4.38 moles of oxygen. We divide by the smallest number, and we get 1 to 2.5. And we have a fraction there, so we have to have whole numbers, use discrete mathematics. So we multiply the ratios by 2, and we get dinitrogen pentoxide as the, well, at least not necessarily that, but the ratio of 2 nitrogens to 5 oxygens. Anybody have any questions with this? It's probably going to be dinitrogen pentoxide, though. It's probably not going to be tetranitrogen decaoxide or something. Okay, so a more advanced one. I used to have this as a chem quiz, but I think I'm just going to go ahead and do it. You guys can watch and learn. So ibuprofen is 75.69% carbon, 8.8% hydrogen, and 15.51% oxygen. What's the empirical formula? So the way you do these percentage ones is you pick any number, and I like 100 grams. That's my favorite number for percentages, because I will then have 75.69 grams of carbon, 8.8 grams of hydrogen, and 15.51 grams of oxygen. And of course, you want to go to moles. So it's going to be mole carbon to 12.01 grams carbon. And again, that's the bottom number in the periodic table, the atomic mass. And mole hydrogen to 1.008 grams hydrogen. And mole oxygen, people are worried about sig figs, 16.000 grams oxygen. And we go ahead and do that. And I did that before I came to class. This is going to be 6.3 moles carbon. Actually, let me move this over. This is going to be 8.73 moles hydrogen and 0.9694 moles oxygen. And what do? We divide by the lowest. The lowest is going to be 0.9694. And we divide each one, maybe I'll put like brackets here. So we divide each of those by 0.9694, and this one's easy. This is 1, 8.73, we get 9, and then 6.5. So to catch you up, we're going to have carbon 6.5, hydrogen 9, oxygen 1. So what do? We multiply by 2 to get rid of the 0.5. And we get 13 carbons, 18 hydrogens, and 2 oxygens. So we have C13, H18, O2. And next thing you do is you check to see, like for me at least, I checked to make sure that ibuprofen is that. So I looked it up on, just, Googled it, and I was right. So I knew I was right there. So, but that is the proper answer. So when you get percentages, the way you solve these problems, it's similar to the other ones, except you pick a value. You can pick something uncomfortable if you'd like. You can pick 27 grams and just multiply it through. Right? I picked 20. I guess 27 is not a prime number. 23, even worse. Pick a prime number if you like pain. Right? You can pick 7. So, but I just like 100 because then I can do the math in my head. So. And then convert grams to moles, divide by the lowest ratio of moles, and then multiply to get rid of the fractions. And then you're done. You have a question? We have a Zoom has a question? What?
Sweet.
Nope. All right, just talking. Yeah. If you can't read this, 1/2 is 0.5. 1/3 is 0.333. It's the Z bar. 1/4 is 0.25, and 1/5 0.2. Able to see what?
Are people on Zoom able to see all these numbers? Because I see that green box at the top, like the green lines.
Yeah.
And
Zoomers, can you see those numbers? Though I just wrote a half. I don't know. You can unmute yourself. We're asking for feedback for your communication.
You can see.
Okay. All right. Just want to check. Your classmates are worried about you. Any other questions? All right. So we're actually again going to move on to chapter 4. And so let me pose a question to you guys. So what do you think? Does your car run on air or does it run on fuel?
It runs on them making combustions.
True. Well, you could argue both ways, actually. Argue both ways, and I can go over a couple of the arguments right now. I know gasoline is a mixture, and it depends on which state you're in and which country. We have 50 states in the union, and we have 50 different blends of gasoline. I don't know about the territories, and I don't know what Washington D.C. does either. Actually,
there's Nutella, or I think there's also some sort of.
Well, it's wonderful you have Nutella, but if you wouldn't mind, please.
Sorry.
So I just picked octane. So octane is 114 grams per moles. Oxygen 2 times 16, 32 grams per moles. I know I'm truncating the numbers a little bit. Carbon dioxide is 44 grams per moles. Oxygen or water is 18 grams per moles. If you balance the chemical equation, well, here you have. I guess we didn't learn how to balance chemical equations yet. So I guess we'll do that next. So I've gone ahead and balanced the chemical equation. And I'll go over this in much more slower detail. But we have 8 carbons. Well, we have 8 carbons, and we have, well, actually, I'll balance this later. I'll go over how to balance the equation in a second. But I wanted to use this to illustrate a few points. First of all, well, this is a balanced chemical equation. There are the same number of atoms on both sides of the equation. So, and if you look at mass, so one thing about chemical and physical processes, mass is conserved. So that's the law of conservation of mass. I know mass does not necessarily have to be conserved, but it can be not conserved in nuclear reactions by E equals mc squared. That's an advanced topic. But for chemical and physical processes that most of us deal with, matter is conserved. So, which means, so we could calculate the formula mass for octane, and there's 2 of them. So we have 228 grams of octane, and we have 25 oxygens or 800 grams of oxygen. So together on the reactant side, so looking at this chemical reaction, the left side is the reactant side. We have 1,028 grams of reactants. The chemical reaction happens and is indicated by the arrow. So we have reactants, and now we have products. And the products, we have 704 grams of carbon dioxide and 324 grams of water. Add those up and you get 1,028 grams. So we have 1,028 grams of reactants and 1,028 grams of products. So you can see matter is conserved. So a couple of things of this. What are the so what's in this? So we've let the talk out for a bit for this. We're talking about doing taxing carbon credits. So taxing carbon dioxide. And so people are wondering, for instance, if you burn a ton of coal, you generate about 3.5 tons of carbon dioxide. So how is that possible? Well, coal is mostly carbon. That's 12 grams per mole. Carbon dioxide is 44 grams per mole. So the mass is increasing. So that's one thing also with the carbon credits. So you wonder like, oh, what's going to happen? One of them is coal is going to become much more expensive, at least as far as electricity generation. So some other things with this. I remember I was a consultant for a billionaire, a guy named by the name of Robert Addington, and he's obviously in the coal, and we were talking about carbon credits, and I wrote this equation on the board, actually the same numbers, and I started talking about them, and Robert, he's a very, very intelligent man, does not understand his chemistry at all though, but that's okay because he hired me to do some chemistry for him. And he had some really interesting ideas. So we're talking about carbon capture, and he goes like, what if I just took my truck, I had a balloon, I had just captured the exhaust of the truck in a balloon. I was like, well, first of all, I'm like, well, if you have a 2-liter engine in your truck and it runs at 3,000 RPMs, right? So that's 3,000 times 2, that's 6,000 liters of air that you're pushing through the car. You're gonna have a really big balloon in a very short period of time. He's like, all right, well, that's not a good idea. So then also he's like, well, what if we took the carbon dioxide and mixed it with calcium hydroxide and then made calcium carbonate, and then we can use that for shipping and like for building materials. And so I calculated it down, and I mean, so calcium, that's how you make, if you wonder how you do cement, you take lime. Lime is calcium oxide, and you wet it, you put water in it, it turns into calcium hydroxide. Then that reacts with carbon dioxide in the air, it turns into calcium carbonate. So that's if you ever made cement or concrete. That's you wet it up and you mix it and you put it down, you let it cure. The curing reacts with carbon dioxide in the atmosphere to form calcium carbonate, CaCO3. So it goes from CaOH2 to CaCO3. And also water pops off, obviously, too. So, and I calculated down that it would add a huge amount of mass to the car. And I kind of just by ratios, I'm like, your gas mileage will drop to somewhere between 5 and 10-ish miles a gallon. You're like, oh, that's a bad idea too, kind of thing. So, and he said, well, what about freight trains? Freight trains run on oil, like kind of low quality fuel oil. And then he was excited about that. Like, yeah, we use it for freight trains then. But actually, on a side point, he was really excited about carbon credits because it was in Appalachia. This was in Kentucky where I was doing the consulting, and they strip mine there, meaning they just rip the top layer of soil off, grab the coal, and then move on. Well, they have to plant trees. So, and an acre of woods captures about 20 tons of CO2 per acre per year. So he was doing some calculations, and it looked like that the carbon credits were worth more from the planting of trees than the actual coal was. He's like, this is a great idea. We need carbon credits. So it's interesting the way things work that way, But anyways, so, and if you're wondering, like, why would this man decide to get a PhD in chemistry and actually, to be quite honest, you shouldn't say this to, if you take speech class, you shouldn't say this. This stuff's kind of boring. This is all chemical accounting stuff. It's not the most exciting thing, but it's exciting when you tell a story and you can apply it to something like carbon credits. So it's enjoyable for me to talk to someone about carbon credits and then apply it to something like a car and what's feasible and not feasible, or something like mining for coal. That's interesting. I don't sit in the corner. I'm not doing calculations going, yes, 44 grams per mole. It's awesome. But it is interesting. The really cool stuff, I'm actually really excited. I like the quantum mechanical stuff. That's the stuff I think is really cool. So we'll get to some of that this semester. I think that's really cool. This stuff, please bear with me. I know it's a little boring, but it still tells a bit of a story. And this is the story of the chemical equation. So we have a chemical equation here, and it does tell a story. This story here has 2 parts octane plus 25 parts oxygen makes 16 carbon dioxides and 18 waters. And these, and it's kind of like a recipe. So if you ever, like I've been doing this more and more with pandemic, right? I'm getting tired of eating the same recipes I do. I start looking in a cookbook and saying, oh, yeah, I could, make some Indian chicken, why not? And there's a recipe there. But the recipe, we have them in chemistry class too as well. But the chemical reactions, they tell you a bit more than a recipe, right? A recipe just tells you, like making pancakes. There's a simple one. I think it's like 2 cups of flour, 1 cup of milk, an egg, and like either salt and baking soda or something like that. And you mix it together and then you make pancakes. So, but instead of using volumes of things, we have specific compounds and elements in the case of oxygen. We know the atomic ratios, so the ratio of the different atoms. And when it's balanced, it obeys the laws of conservation of mass and definite proportions and multiple proportions if applicable, right? So there's a lot of information in a chemical reaction or a chemical equation. So, and also if you do go into chemical industries, there's a bit of industrial espionage that can go on. And one of the most coveted things is actually the mixing sheets. So if you go to a chemical plant, and I spent a summer, you ever heard of Ecolab before? They make industrial soaps. I worked as an intern at Ecolab, and they were telling me all right, these are the things that people are going to go after. It's going to be the mixing sheets. I don't know why I didn't steal any, of course, but I mean, like a recipe. I mean, we're required by law to give the recipes for things, right? I mean, you look in the back of any food or cosmetic product, right? And the first ingredient is always water, right? It's water, sodium lauryl sulfate, and all these other things, it just lists the different ingredients. And by American law, you have to list them in order of concentration up to 1%, and the order doesn't matter. So, and that's another trick I learned. I guess I didn't tell this class. Did you guys know that I used to work at Bath and Body Works? Yeah, I was Bath and Body Works in Victoria's Secret. My father worked there, and I worked there for 3 summers. And one of the summers I did labeling laws. So that's the reason why I know the labeling laws. So I did quality control, process engineering, quality assurance, which is labeling laws. Oh, and I did packaging. I guess the first thing I did packaging engineering. I had to drop boxes, make sure nothing broke. So it's kind of like, it was an intern appropriate job. I wasn't doing major calculations of drop this, make sure it doesn't break, that stuff. But anyways, yeah, so, then after Bath and Body Works, it's Victoria's Secret's the same company too. So it's interesting the way marketing works, because at Bath and Body Works, I haven't gone to the store in quite a bit. They had a scent called Plumeria. I don't know if they still have that. And then it's the same scent at Victoria's Secret, but it was called Island Passion. And they sold it, the Bath and Body Works was 8 ounces, and the Victoria's Secret was 4 or 6 ounces, but it was purple instead of pink, and they charged more for it at Victoria's Secret. So, and I think it actually outsold at Victoria's Secret than it did Bath and Body Works. It's the same stuff, but hey, marketing, what can you say? But anyways, so if you do work in an industry like that, one of the things they'll really go after are the mixing sheets. So meaning when you make something, and I'll talk about this probably next class, we make things in huge quantities. So thousands of gallons, tens of thousands of gallons. You don't make 2 bars of soap, you make thousands of them at the time. So, and how do you make them? You have the mixers also. You have the chemists that make the formulation, and then you have the mixers. The mixers actually tend to be high school educated or less. So, and their job is actually really dangerous. They got paid a lot. They got paid a lot, but they also had a dangerous job because there was a huge amount of chemical exposure to them. And not only that, they didn't know what they were getting exposed to. So chemists, on the other hand, chemists rarely get occupational illnesses. What is occupational illnesses? So cancer. Cancer is one. Other one is contact dermatitis. That's forever inflamed skin. I mean, you can get dermatitis, other things. Poison ivy gives me dermatitis. But contact dermatitis, that's if you get chemical exposures over a long period of time, you can get forever inflamed skin. Cosmetologists, so hair cutters, they get a lot of contact dermatitis. Actually, almost all of them do if they work in the career. But the mixers, what they would do is they would have the mix sheets, and they would say things like put 20,000 gallons of water into a tank, then add 50 gallons of sulfuric acid, stir it for 5 minutes, add 20 pounds of sodium hydroxide, stir it for another 20 minutes, and just went down the list of things to do. And like, what was nice about the mixing sheets are, they not only told you the formula, because you get the formula from that, but they also told you how to make the stuff. And that's hard. That's hard to figure out how to make the stuff. So that's like I said, with industrial espionage, a lot of people try and steal secrets here and there. But okay, so I'll go into a little bit more about industry later, but let's learn about how to balance chemical equations. So here is a simple reaction. Methane, CH4 plus oxygen makes carbon dioxide and water. So, and it's already balanced. So let's say we didn't have these numbers, and I guess, so how would I balance this chemical equation? So I would see, okay, there's one carbon over here. I always pick an element, I balance it with respect to that element. There's one carbon here, and there's one carbon here. That's easy. Carbon's already balanced. And then the next one, I'm going to pick hydrogen. Why don't I pick oxygen? Because oxygen is on one compound here. Well, it's an element. It's on two over here. Trying to balance with oxygen is going to be a little more difficult. So I'm going to pick hydrogen. And there's 4 hydrogens here, and there's 2 hydrogens here. So what do? Do I say, okay, we're going to make H4O? We can't do that. We can't say we're making H4O because H4O is a different compound. It doesn't exist actually. So how do I have this compound that has 2 hydrogens in it? How do I turn it into 4 hydrogens? I multiply it by 2. So I don't change the number of atoms in the compound. I change the number of those compounds I make. So I've made now 2 waters, and because of that, I have 4 hydrogens. Now let's balance oxygens. I have 2 on the left, and so I have 2 from carbon dioxide, and I have 2 because there's implied a 1 there. So 2 times 1, 2 waters means I have 2 oxygens, and then so if I have 4 oxygen on the right and 2 on the left, how do I make sure there's 4 oxygens on the right? Then I multiply the oxygen by 2. And I guess I've also said something. So the right side is the products, and the left side is the reactant. I think I misspoke. 2 oxygens on the left on the reactant side. So left is reactants, right is products. And it's also it's even illustrated here with pictures. So there's pictures here, and you can see here, there's the methane molecule. We'll learn about this more near the end of the semester. Right now, you don't have to learn about this. We're going to cover bonding and Lewis structures later. And then these are 2 oxygens here. So if you've had high school chemistry, you probably already know about this. And here's carbon dioxide here. So carbon dioxide, it's a molecule that has, I just drew its Lewis structure. It's got 2 oxygens and 1 carbon. It's actually got the carbon in the center like that. But again, we'll learn more about that later in the semester. And then water here, and I'll draw the Lewis structure. It's a bent molecule like that with the hydrogen. The white balls are hydrogen, the red is oxygen, the black is carbon. And if you count, you can also count the numbers, right? So it's easy with the black balls. There's only one on the left and one on the right. So one carbon. Hydrogens, 1, 2, 3, 4 there. 1, 2, 3, 4 there. Okay, that's good. And then let me change colors here. I should do green. I guess green shows up better. So 1, 2, 3, 4 on the left, 1, 2, 3, 4 on the right. So the oxygens are also conserved. So that tells you about balancing chemical reactions. You can't change the compounds. That's a common mistake students make. So you have to keep the compounds, and then you have to make sure that there's the same number of each type of atom on each side of the chemical equation. So how are we doing so far? Anybody have any questions? All right, let me do this then for this. So we have C4H10 reacting with oxygen, combustion with oxygen to form carbon dioxide and water. So this is a very common reaction. It's known as a combustion reaction. So let me start off here. We have 4 carbons here. So we have to have 4 carbons there. So now I'm going to balance the hydrogens. We have 10 hydrogens here. So we have to say 5 waters there, because 5 times 2 is 10. And you can already see there's going to be a problem because there's an odd number of oxygens. But I'll just carry through. So now oxygens, there's one molecule that has oxygen on the reactant side, product side. Let me count the number of oxygens. So we have 4 times 2 or 8 oxygens. And we have 5 times 1 or 5 oxygens. So now we have 13 oxygens. And there's a couple ways you can do this. And I know I confuse people. I kind of made a mental note last class to try and not give you several different ways to solve the same problem. Although that is the way my brain works. But I'll try and limit that. You can go ahead and multiply it by 2 right now if you want. But I'm just going to balance it straightforward. So the way you can balance this, you can say we have 13 halves. So balancing 13 oxygens on this side of the equation means you need to have 13 halves oxygen molecules on the left. So of course, as mentioned before, discrete mathematics, we can't have fractions. So then we multiply this whole thing by 2. And in doing so, we get 2 C4H10. I'm not sure. I'm not naming the molecule because I'm not sure if it's cyclized, if it's with branched. I'm not sure. So 13. You'll have 13. We're going to have 8 and 10 here. So let me check. So let me check with the carbons. Here on the left, maybe I'll stick with the color scheme. Carbon's black. 2 times 4 is 8. And 8 times 1 is 8. So the carbons are balanced. I'll do red or green for hydrogens. So 2 times 10 is 20 hydrogens. And 10 times 2 is 20 hydrogens. So hydrogens are balanced. And then red oxygens, 13 times 2 is 26 oxygens. And then we have 8 times 2 or 16 oxygens, and 10 times 1 or 10 oxygens, 16. That's an O. 16 plus 10 is 26 oxygens. And you can see 26 on the left, 26 on the right. So we've balanced it completely. We have the same number of atoms on both sides of the chemical equation. So how are we doing so far? Questions? No questions. All right. Time for you guys. see if you can figure this out. So how many waters? What is this coefficient? The one right before H2O. How you guys doing in Zoom land or Zoomers, or what I call you, Zoomers?
We're good.
Sorry, Mr. Ferguson, that says C6, H15, yeah.
C6, H13.
Thank you.
It doesn't say B. Do you think it said B or something like that?
No, I'm sorry. It just is covering on my screen, so
No.
sorry.
No worries. Simple question, simple answer. I hope all the questions are, well, I shouldn't say that simple. Requires minimal brain power by me. Okay, how many people think it's A, 6.5? I think B, 13. How many think C, 26? How many think D, 24? Okay, people are not answering. We had a few for 13, a few for 26, but I'm gonna kind of go around social distance wise. Is anyone completely lost and doesn't know how to do it? No one's lost. Okay, you just need more time. Well, I guess the feedback I'm getting, actually, it's hard to read, you guys. I don't know where you're getting stuck. So right away, though, I mean, just looking forward, you have 13. You have 13 here, and you have 2 here. So right away, you know you have to multiply by 2 because you have an odd number on the left and an even number on the right. So you might as well just start off by multiplying everything by 2. Right, so now when you start by balancing the carbons, so 2 on the left, you have 2 times 6 or 12 carbons on the left. So you need to have 12 carbons for the carbon dioxide. Now balancing the hydrogens, you have 26 on the left. So you need to have 26 on the right. And the way you do this is put 13 here. And if you're looking ahead, you're like, okay, well, I now have an odd number of oxygens, right? So 12 times 2, this is 24, but 13 times 1, that's 13. So that's 37. 37 oxygens over here, right? So 12 times 2 is 24. 24 plus 13 is 37. The OX. My O's and my zeros look exactly the same. So you have 37 oxygens on the right. So which means when we balance it, we'll have 37 over 2. And now what do we do? How do we get rid of that? We multiply everything by 2 again. And so that means we get 4, 37, 24, 26. So the balanced chemical reaction has 26 waters.
Okay, I think for the oxygen, you said you got 37. I think that's where I got
Okay. Because oxygen's on 2 molecules. By 2, yeah. By 2 because, well, are you talking about by 4? Well, because I had to multiply by 2 twice. Right. And the reason why I had to multiply by 2 twice is because of odd numbers. Yeah. Because remember, discrete mathematics, you got to have everything. We can only deal with specific numbers of things. I'm usually pretty good at reading people's faces, but I'm having a really hard time reading your guys' faces. Are you understanding? Do you have any questions? Please let me know. My job is to teach, and I'm usually better at this. I mean, even worse for you guys, Zoomers. I have no idea what you're thinking, unless it's, do I need to get off the couch or something like that? That's usually what I'm thinking when I'm on Zoom. I wonder what the cat's up to. You have a cat. Probably sleeping. Yeah, I'm sure the cats are sleeping right now. So, anybody have any questions? No questions? Nothing? Okay, so I will just move on then. Let me go back up and talk about, does the car run on air or fuel? I mentioned that before. So does the car run on air or fuel? I said there's arguments for both. So one of the things is that there's so much oxygen around. You really, I mean, kind of the logical sense here on Earth is car runs on air, on fuel, duh. Right? Come on, you run out of fuel, you fill the car back up, you keep on driving. You don't really worry about the atmosphere running out of oxygen. But by mass, your car runs on air much more than it does on fuel. So almost 4 times, it requires about 4 times as much mass of oxygen as it does fuel to run your car. Well, where might we be concerned about this? So where might we be concerned? Yeah.
What constitutes as air? Isn't the oxygen
Yeah.
mostly nitrogen?
Yeah, but it's a component. Yeah. It's 1/5 of it, well, 20.5% of the atmosphere is oxygen on average. So, but there are certain occasions where we might worry about if there's enough oxygen, and that's for space travel. So, right, the thrust that we get for rockets is usually combustion. Actually, there's only a few circumstances. Sometimes we use celestial objects for catapulting things with gravity. We're experimenting with other types of propulsion, but it's pretty much just combustion or some sort of reaction that pushes the thrust. So if you're in a spaceship, you have to worry about that. And this is building up to another concept called the limiting reagents. So what I'm also saying is when you drive your car, what you're limited by is the fuel. You don't worry about the oxygen because there's so much oxygen. There's an excess of oxygen. But the fuel is the limiting factor for that. But before we get into that, let me bring you back to childhood. So how to make a Happy Meal. And I guess I've gotten old. I guess what constitutes a Happy Meal has changed. Has it changed again? Is this what's in Happy Meals?
There's 4 night figures.
There's what?
4 night figures.
That's a toy.
Yeah.
Yeah. So.
Never milk and never apples. I've never seen that.
Oh, really? Okay. Well, let's erase this. What's in a Happy Meal? So someone who's educated in this subject. Do we have any Happy Meal experts? Okay. Oh, we are over Zoom land. I'm sorry, you're overridden. There's an apple and there's milk. What else is there?
Nuggets, if you want. Burger or nuggets?
Let's go with nuggets. Fries. Would you say fortnight? What the heck? Am I spelling this correctly? Is it like that? Okay. All right.
Yeah.
So if I have 10 apples, 10 things of milk, 10 whatever, how many nuggets is it? 6 or it doesn't matter. 10 satchels of nuggets, 10 fries, and 1,000 fortnight things. How many Happy Meals can I make? 10, but I've got 1,000 fortnight toy thingies. How come I can't make 1,000? I have enough toys to make 1,000. Am I limited by something? You know, of course, yes, you are limited. There is something limiting how much you can make, right? So in this case, it's everything else. Let's say I have, I'll do 100,000 apples. We like our apples here. How many chicken nuggets can I have here? Or how many Happy Meals can I make now? Still, but I have 100,000 apples. Yeah, but yes, you're still limited by something. And whatever it is you're limited by, that is exactly how much you can make. So we have a limiting reagent here. And also, let me go over another example of something. So how about a ham sandwich? So this is, I know it's not necessarily a reaction. It's just, something, a product made by putting two things together. But we have ratios, as you can see, we're building up the chemical reactions. So what if I have 1,000 pieces of bread and 1,000 pieces of ham? How many ham sandwiches can I make? 500 ham sandwiches, right? Because I need 2 pieces of bread, and I'm miming this, Zoomers, I'm miming my hands as pieces of bread with my Apple Pencil case to make the ham sandwiches, right? So I have a 2-to-1 stoichiometric ratio of bread to ham. So you have to keep that into consideration as well when you're doing these, is that sometimes you have ratios of reactants to form a product. Of course, we have 500 ham sandwiches, but we will also have plus 500 excess ham slices. So, I mean, those are also there. So I'm going to have excess in that regard. So we have we have how much we can make, how much product we can make, and then we have a certain amount of excess. So depending on this, it's very rare to have exactly the same amount of things. It's like buying containers of hot dogs and buns at the grocery store, right? They actually mismatch that on purpose, so it's hard to get the right ratio. So you have to buy more of one. So this is a limiting reagent. I think you're starting to get it. So let's start with a limiting reagent problem here. And this is an example of one where you have excess. So meaning it's not difficult to figure out what the limiting reagent is. So during photosynthesis, plants convert carbon dioxide and water into glucose according to the reaction. The photosynthesis reaction, as a matter of fact, 6 carbon dioxides plus 6 waters reacting in sunlight makes 6 oxygens and glucose. And suppose that a particular plant consumes 37.8 grams of carbon dioxide in 1 week, assuming there's more enough water present to react with all the carbon dioxide. What mass and glucose can the plant synthesize from the carbon dioxide? Okay, so unfortunately, my PhD is in chemistry and not in art. So here is my artistic drawing of the chemical reaction. So we have a vessel that has some, I'm guessing it's algae. It's probably algae. And we have some water in there, and you have that, and it reacts, and somehow you measure the amount of carbon dioxide that's in there, and you find out that the amount of carbon dioxide has gone down by 37.8 grams. So we're looking at this. We are attacking this problem. We have 37.8 grams of carbon dioxide that's given to us. We're also given, in this case, the balanced chemical equation. And we also, the product, glucose. We want to know the mass of glucose. So we're doing dimensional analysis. So we're going to do 37.8 grams of carbon dioxide and then multiply by, so always think of moles CO2. And I know it's 44. Let me go, I'll go with the book. Just so 44.01. 44.01 grams CO2. So now we go to moles CO2. And now this next step, this is going to be new to you. So we're going to have mole glucose. Well, I guess this is the shorthand for different sugars. GLU is glucose. Mole glucose. Maybe I'll just write it out. I'll not confuse you with chemistry notation yet. Mole glucose to 6 moles CO2. So this is a new step. So this, and let me circle it. This step right here is a new concept for you. So you have a balanced chemical equation, and now with a balanced chemical equation, you can give ratios of reactants and products to other reactants and products. So in this case, we'll zoom in. For 6 parts CO2, we get 1 part glucose. So, and this again, it only works for a balanced chemical equation. If you have the chemical equation as balanced, you'll get this ratio wrong. So that's why it's important to have a balanced chemical equation.
Will it say if it's not balanced?
Well, it's usually human error. Like, what if I was having a case of the Mondays and I wrote 7?
Got you.
Do you get that reference?
No.
Oh man,
Case of the Mondays?
Office Space.
No.
Oh, how do I reach these kids? Do you get that reference?
Fortnite.
Ah, there we go. Didn't know this was gonna turn into a history class. All right, sorry, I'm the old one here. I'll stop my old man talk with movie references. Okay, so now where are we at? We are at moles glucose. Remember, we're trying to go for the product, which is massive glucose. And now that we have moles of glucose, we have 180, is it 180 something? 180.2 grams of glucose. Just C6, sorry. C6H12 to mole glucose, C6H12. I'm so lazy, I just want to write GLU for glucose. So actually, in some ways, being lazy is a virtue. I remember one of my teachers saying that laziness is a virtue. So, so for this one, now dimensional analysis, check to see the units. So grams, carbon dioxide cancels, moles cancels, these moles cancel, and we're left with the units that we want is in grams of glucose. And then doing this, we then calculate out that this is 25.8 grams of glucose, C6H12O6. Okay. So recap with this one. So we have an experiment that we're trying to figure out. Somehow in this experiment, we figure out that the plant consumes 37.8 grams of carbon dioxide. And we want to figure out what mass of glucose this plant generated in the meantime, doing that via the photosynthesis reaction. So we picked dimensional analysis as the easiest way to do it. 37.8 grams of glucose, convert to moles of, 37.8 grams of carbon dioxide, convert to moles carbon dioxide. The new step, the 1:6 ratio of glucose to carbon dioxide from the balanced chemical equation. And then the formula mass for glucose, we get 25.8 grams of glucose as our answer. So, questions with this, how to solve this? Again, the new step is the one in the middle there, the mole, the 6:1 carbon dioxide to glucose ratio. That's the new concept here. The other thing is that I'm building up to is the limiting reagent. So you have two reactants, carbon dioxide and water. And the idea is that there's an excess of water. So it's like driving your car. You don't worry about the atmosphere running out of oxygen, you worry about your car running out of gasoline. So in this case, we're worried about the carbon dioxide that's being reacted. That's the limiting reagent in this one. So what? Well, we go back to carbon credits, and it was interesting that how things have changed. In the 1970s, there was a huge issue with energy. We were running out of energy, well, fuel. And there was a huge push to looking at biofuels. And we actually developed quite a bit of technology to make algae biofuels. And then around 2008-ish, we were looking at algae biofuel again. So we do use some biofuels now. We use corn ethanol. And so part of the reasons why we use ethanol, it adds more, it has a higher octane rating, it adds more oxygen, leads to more complete combustion. So adding ethanol to fuel actually makes it burn more cleanly. So that's one of the reasons why we add ethanol to fuel. And we get that from corn. And we're also looking to make algae to do other things. And well, there was also the argument for carbon credits. So it was interesting seeing the scientific literature. So one of the things that's nice about the United States is that we have the most beautiful topsoil, especially in Indiana, Ohio, Iowa, Illinois, those states. And the reason is because of the ice ages and the glaciation basically pushes the topsoil off of Canada and plops it right down in the Midwest. And it's done that several times over the past couple million years. So we just have wonderful topsoil. And it was interesting seeing the different biofuels, and because they were trying to do it in Europe as well. The United States outperformed Europe all the time in cropland. We have such wonderful cropland here in the United States. So that's one of the nice things about this country. But you talk about corn, and like I said, the Europeans are like, we cannot reproduce the United States. You guys are just, your topsoil is too good. Then, but then we're also looking at fuels. We still haven't quite figured this out yet. It'd be nice if we could take algae and turn it into things like ethanol. So, I mean, you don't even, because right now the way we get ethanol is you make beer. So, you can make wine as well. That's from grapes, or other fruits. You make beer from corn, and then you distill the alcohol off of that. And you can distill it up to 95%. And then typically we use what's called a molecular sieve. It's a filter that has small holes. You put pressure on the grain alcohol. Grain alcohol is 95% alcohol, and you push out the water. And then you have pure ethanol left over. That's typically how we make it. And but algae, we're looking at algae for a couple things. Actually, on the Big Island, we're looking for food. Although they use a fermentation for that at the Big Island, but we're looking for respiration here using photosynthesis to question.
Yeah, what about cars powered by water?
Oh, that's another plant thing. The water cars are actually they're run off of hydrogen. They use metals or metal hydrides, and then you have to replace the metal hydrides. So
you can't just grab the water.
No. Nope. You have it generates hydrogen from something else, from the chemical reaction. but it's actually worse because solids are harder to deal with. Liquids and gases. Liquids are extremely easy to deal with. Gases are almost as easy as liquids, but a little bit more difficult, and solids are horrible to deal with. They're really hard to work with. So it's actually, you'd be better off driving your car off of natural gas or compressed hydrogen than using the metal hydrides, because the solids are just more difficult to handle. Okay, so that algae we're really looking at, and why are we interested in algae versus corn? Well, I mean, think about corn. When you plant corn, the corn has to germinate, has to grow roots, it has to grow a stalk, fruit, flower, be fertilized, and then you have to harvest the corn. So it's got most of the energy that is absorbed actually goes into other things, goes into growing the stalk, growing the roots, that kind of thing. Algae, though, it's single celled. Divide. Doesn't need to grow leaves, does not need to grow a stalk, does not need to grow roots. And doesn't need to be fertilized either. So you don't need to have bees or other insects to help fertilize, or humans. There are some people that the job is to go and fertilize. They usually do it for research, but you have people that go and they pollinate the different corn. But that's one of the reasons why we're looking at algae. Problem with algae, though, there's two things with algae. It consumes a lot of water. The other thing, I guess there's a couple problems with it. It requires a huge amount of capital. So money, you have to make an open pit, or you have to make the pool for 2-dimensional, or they're looking at doing 3-dimensional. I mean, you have something like a shower curtain, and then it drips, and then you have a bunch of these sheets, and you can have like a whole room, like a bunch of sheets of like algae bioreactors. But they're kind of looking at for that. I think that's where we might go for space travel. So if you're going to grow your own food and oxygen, you can do that with algae. Another problem with algae is that after about 2 weeks, the whole colony dies. So
Really?
Yeah.
Doesn't last forever?
Nope. Usually, yeah. At least when we're doing biofuels, and because the idea is a foreign microorganism comes in and just kills it all.
Bacteria.
Yeah. It starts off okay, then it actually gets better because it evolves to like after like 3 to 5-ish days, the algae colony does great, and it goes great for a while, and then it dies. So we're still trying to figure out how to use algae biofuels because it'd be great, right? I mean, this is a wonderful thing. We could, because we can manipulate the genes, we can use it to make pretty much any food source. So carbohydrates, fats, proteins, we can use the algae to make that. So that's where we're thinking about space travel. We can use it to spit out methane or something else, like you can make good biodiesel from it. So, or even ethanol. We're trying to get it to make ethanol so that we can make all those steps with the corn. Don't have to make beer, which I think is a bad thing, but Anyways, so that's kind of where we're going with algae right now. We do quite a bit of research with this. We used to. I mean, right now, of course, most of our research is going towards COVID, but there was a huge amount of research going in this before. So, okay. Here is another thing. So, have questions, anyone? So, talking about LIMI reagents and theoretical yields. So, we have the ammonia synthesis reaction here. So, nitrogen plus 3 hydrogens react to make 2 ammonias. And I've already kind of written this. If you have a catalyst, oftentimes catalysts are written over the arrow in a chemical reaction. And for ammonia synthesis, the catalyst for this is iron, of all things. So let's do this, and then I'll talk about the applications of this. And so the flask mixture has reactants represented by the image shown on the left, which shows what's the limiting? So which of the following images represent the mixture after reactants have completely reacted? And what is the limiting reagent? And what's an excess? So we have this vessel here, and we can kind of figure out what's going to happen here. So we have 2 nitrogens, 2 N2s, and how many hydrogens we have? Let me see here. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 hydrogens. So from this, we have 2 nitrogens and we have 8 hydrogens. And let's assume now that the nitrogen is the limiting reagent. So to figure this out, we have to figure out what's going to be. Well, actually, for this one, we don't have the right number of hydrogens, so it's going to be even easier. So I'll explain this a little more later, but the limiting reagent in this case is nitrogen. And just because this is the only way, because we have such small numbers, this is the only way that it's going to be divisible by anything. So we have N2 plus 3 H2s makes 2 ammonias, and we have 2 nitrogens, and that's going to consume, 2 nitrogens is going to consume 6 hydrogens, and we're going to make 4 ammonias. And the part of the problem is since we have 8 hydrogens, it's not divisible by 3. So, but I mean, you're not going to have this number, such small numbers of things, at least not really practically. You're going to have huge numbers, of course. So what we're going to have react, so since we start off with 2 nitrogens and 8 hydrogens, and then 2 nitrogens react, 6 hydrogens react, we're going to have 2 hydrogens left over. So we're going to have, that's the way this chemical reaction is going to go. The limiting reagent is, so this is the, this is the limiting reagent. LR is, limiting reagent is nitrogen, and then this is going to be the excess. So the hydrogen is excess. And so which one of these does it fit? Well, if you look at A, this hasn't reacted all the way. So that's actually in the middle of the reaction. B, we do have 4 ammonias, but we actually have excess hydrogens. But C here, we have with C, the letter C, we have 4 ammonias and 2 excess hydrogens. So this is the proper one, assuming that all of this has reacted. So that is the proper, yes, question.
Is it for all nonmetals or, but I noticed that the hydrogen, oxygen, and nitrogen, they tend to pair up with each other. Does that happen with all elements or just the gases?
Check on as far as its elemental forms.
Well, like there's H2, yeah, into the molecular.
They're diatomic, you mean?
Yeah, I guess.
The question is, do the nonmetals form diatomics? And the elements that form diatomics are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are the ones that, and their ground states, form diatomics. You can form diatomics for the halogens. These can form diatomics under certain circumstances. They're not considered the lowest energy state. You can get certain non-metals like ruthenium, for instance, will form a diatomic, but those are more in unique circumstances. So, but generally speaking, for the ground states, the elements that I think the question you're asking, the ones that form diatomics is going to be hydrogen, nitrogen, oxygen, and the halogens. So carbon, its ground, so we call it the lowest energy state. Its ground state is graphite. Phosphorus, there's 2 forms. I forget which one is what we consider a ground state. Sulfur, I think forms S6 is what its ground state is. I could look that up. It's not diatomic though. And the noble gases are just atoms. They don't tend to form bonds. You can get helium, you can get diatomics of these, but they're also under certain circumstances. So I have a bad habit of giving dollar answers in nickel questions. So Other questions? Okay, and briefly, I know we only have 5 minutes of class left and not going to go into the next part here. So I did say that we're talking about history, but I'll talk about history not in terms of crappy movies. Has anyone, maybe even philosophy, has anyone heard of a Malthusian catastrophe before? Anyone heard of the philosopher Thomas Malthus? So a Malthusian catastrophe is when a society outgrows its ability to feed itself. So what Thomas Malthus said was, if you look at population versus time, it's exponential. And also food production. So food, it's arithmetic. So meaning if an acre of corn, actually an acre of corn can form about 400 bushels. Let's say, let's do something simple. An acre of corn can generate 100 bushels of corn. How do I make 200 bushels? I plant 2 acres. If I want to make 400, I plant 4. So that's what I mean by arithmetic. Population, on the other hand, so if you look at generations, so if you look at my grandparents on my mother's side, they had 8 kids. And then the number of cousins I have, including myself, is 27. Well, if you count my siblings, a cousin, that's 27. I don't know about the next generation, but I know there's 11 in my family. Well, 2 adopted, so 13, depending on if you want to include that. So, and that's just one of the 8 families, and assuming, the same ratio, right? We're looking at over, 80 to 100 in the next generation. That's what I mean by population growing exponentially. So you get to a point, though, where you cannot feed the population. And that's known as a Malthusian catastrophe. And if you look at human history, so population versus time, it kind of looks like this. And right about here is about the year 1900. So we went from a population of 2 billion in 1900 to, 7, 8-ish billion now. So, like in 120 years, we've doubled twice our population. So why do you think our population has doubled since the year twice since the year 1900?
Because it's exponential.
What's that?
Isn't that when they have like the
Industrial Revolution, yes, that's part of it. And medicine's another one. And there's something?
Oh, well, medicine, we also travel.
Not so much travel. Yeah, the Industrial Revolution, meaning we mechanized our agriculture. And one of the things, and what we were limited, we actually had an issue with a limiting reagent. The limiting reagent was nitrogen fertilizer specifically. So the invention of nitrogen fertilizer was a huge thing. Suddenly, that's the reason why we're all getting fat, is because of the huge excess of food. I also mentioned medicine, very important in the 1930s-ish was the invention of antibiotics. So antibiotics caused more people to survive and to survive into their reproductive years. So a lot of people died as children. Also vaccinations. I think antibiotics are more, my own personal opinion, I think the antibiotics is more important than the vaccinations, but the vaccinations certainly have helped. Got rid of a lot of childhood diseases, but they tended not to be very lethal. But bacteria is extremely lethal. Like if you look at why people died back in the year 1900, it's going to be pneumonia, septicemia, so infectious disease. Now it's cancer, and that's my shut up alarm. Okay, shut up alarm.